All right, I think I'm live now. Great. Welcome, everybody, to the plenary session talking about planetary defense. Everybody, please come on forward. There's still plenty of seats up front, and those of you that are outside, come on in. Je m'appelle Deepak Srinivasan from the Johns Hopkins Applied Physics Laboratory, and today we're going to talk about planetary defense. Last night, if any of you guys were at the highlight lecture, we had two wonderful scientists talk about two bold missions to study our sun and learn about space weather, one of the natural space hazards that we have to deal with. We learned a lot about how collaboration from different points of view are enabling us to protect ourselves. In this panel, we're going to talk about another space hazard out there, asteroids. The funny thing is, I'm actually an RF engineer, and there, see? Made it work. So the good thing, actually here we are. As you can see, asteroids, they come in all shapes and sizes. And there's a lot to unpack on this chart, but it's a pretty intuitive chart. The bigger the asteroid, the bigger the damage. I want to draw your eyes to the bottom of the chart, though. That talks about how many of these asteroids have we actually found, right? The large asteroids, we found a lot. Small asteroids, not as much. When we want to figure out how to mitigate against asteroids, we take a very project management type approach and look at the risk, consequences, and the likelihood. We're not really too worried about the small asteroids. Even though we haven't found a lot of them, they're little babies. It's harmless. You just brush it off. It's a flesh wound. Likewise, we're not as worried about the largest asteroids. Yes, they can be devastating, but we found the vast majority of them. We know where they are. We're tracking them. We're not on a collision course. We're good. What we really want to worry about are the asteroids that are in that size range of what we saw in the movie, 50 to a few hundred meters or so. Those are the ones that can cause a significant amount of damage at the city or even regional level. These are what we have to protect against, and these are also the ones that we haven't found a whole lot of them. That's the bad news. They're out there. Good news is that we have both national and international strategies on how to deal with that. We're going to hear a lot about that from our esteemed panel here. Bhavya Lal is going to kick off our discussion. She is the Associate Administrator at NASA, dealing with a lot of the technology, policy, and strategy issues. She's going to talk about NASA's, as well as the United States' plans on how we're going to be combating this. Following her, Richard Moisel, who is the head of the Planetary Defense Office at ESA, is going to discuss the plans that the Europeans have. My colleague, Betsy Congdon from APL, she will be talking about the upcoming DART mission, which you guys are going to be hearing more and more about over the next week leading up to its impact. Following her, Patrick Michel, who is the principal investigator for Hera, that's ESA's follow-on to DART, is going to give us an update on what they're doing. Then lastly, we have my friend and colleague Bill Nye, CEO of the Planetary Society, to talk about how all of us can take part and contribute to this overall effort to literally save our planet. With that, I'm going to turn it over to Bhavya. Thank you.
Thank you. Good afternoon. Deepak, you've set the problem up so well, although the video did a pretty darn good job as well. So,
Yep.
So I'm here to tell you about NASA's efforts in the area of planetary defense. And I want to start with something that we are doing at the White House level. So in 2018, the Office of Science and Technology Policy developed a national Near-Earth Object Preparedness Strategy and Action Plan. Again, just a term of art. We've been talking about asteroids. Near-Earth objects are asteroids and comets that can come, dangerously close to Earth, and that's kind of the NEO is the term of art that's used. So the NEO Preparedness Strategy and Action Plan has 5 goals: enhance detection, characterization, and tracking. We cannot stop an asteroid if we don't know where they are. Improve modeling, prediction, and information integration. You saw some of what you saw in the video was actually some of the modeling that is going on. And again, not everything that is done in the United States on planetary defense is at NASA. So a lot of the work is done, a lot of the modeling work is done by the Department of Energy. Third, we want to, it's not enough not just to know where the where the asteroids are, where the NEOs are, or where they're headed. We also want to be able to deflect them and disrupt them. And by disrupt, I mean basically, explode them if that is what's needed. And the fourth, very important, planetary defense is a global enterprise. We need to be working globally, and as the panel shows here, we already are, but we need to do more and better. And last but not least, if an asteroid does hit us, we want to make sure that we have a process to coordinate things like evacuations or post-recovery, and also collaborate with the rest of the world to do something similar. NASA was prescient even before the planetary defense strategy came out. We had developed a planetary defense coordination office led by Lindley Johnson, who is its head, and it was established in 2016. And let me actually just say what it is that we do by these 5 activities. So the first thing is we search, detect, and track. The thing that you see on the top right. We must find any hazardous asteroids or comets. We cannot do anything until we know where they are. Second is the characterization, which is often underestimated. There are several projects that are supported by the Planetary Defense Coordination Office to better understand the nature of these asteroids and comets. We need to understand their size and composition. If an asteroid is made of, for example, loose gravel, it may not, the approaches to disrupt it may be different than if it was, metal or some other kind of rock, right? The next one is the planning and coordination bit. Many of the activities of our Planetary Defense Coordination Office are not just within NASA, but across the US government and with international partners. So for example, if an asteroid is likely to hit, we need to work with the Department of Homeland Defense, in particular, the Federal Emergency Management Agency, FEMA, that will work with local government agencies to figure out what needs to happen when, how do we work together with other communities, how do we work together with the rest of the world. Next, we need to mitigate the effect of these asteroids. These are efforts focused on testing and exercising methods to either deflect an asteroid impact in space, and actually we are going to talk a little bit about the DART project, the DART mission, or we need to prepare to take a hit on the ground if the object is too small or found not soon enough to attempt an in-space deflection. And an example was the NEO airburst that happened over Chelyabinsk in 2013. We did not see it coming until it was nearly there. So we need to be able to plan for those sorts of things. And finally, we must conduct efforts to assess our level of success and comprehension of these other 4 sectors. Monitoring the NEO survey efforts to track their progress at finding the existing population, which is actually conducted by the Center for NEO Studies at the Jet Propulsion Lab, is an example of this. So moving on, again, this is not just a US activity. NASA works with the International Asteroid Warning Network. It's an international body. We also work with this organization called the Space Mission Planning Advisory Group, or SamePage. In fact, the DART mission and the Hera mission came out of SamePage activities. The I-1 is currently coordinated by NASA and has 40 signatories from around the world. And SamePage is chaired by ESA currently and has 18 national space agencies or offices as members. We have 3 minutes left. I will speed up. So just for you to know where these survey telescopes are, they are all over the world. And one thing I wanted to point out was more than 90% of the asteroids or the NEOs that we have discovered have been discovered by one or more of these assets. One you see in the corner is called NEOWISE, which is not on the ground, it's in space. And I think this is where we need to start to think about what is next. So many of these asteroids, especially the smaller ones, are hard to find from the ground. And that's because, and actually I will tell you why that is. Look at this animation. So you have 2 asteroids, one on the left, one on the right. As they go farther in the distance, one of the asteroids is no longer visible. And this is what happens when you're only looking through visible light. However, if you look through infrared light, you will see that you can track both of them as well. And one of them is a highly reflective asteroid, and the other one wasn't. But in infrared, they're both the same. And what we need to do is to have infrared telescopes. Unfortunately, you can't have those on the ground. You need to have them from space. And that is one mission that we are working on. It's called, actually, let me just finish the animation. It's called Neo-Surveyor. It is basically going to sit at the Earth's and L1 point. And unlike the ground-based assets that actually, hang on.
Go back.
Go back. So the right side, basically Earth-based assets only look at ground-based assets, look away from the sun. The black area on the right, we have this little teeny field of regard that the NEOWISE, which is actually at the end of its life. So Neo-Surveyor is actually going to really be able to give us this broader field of regard. We are going to be able to discover most asteroids 140 meters and above, instead of in 30 years, which is what might have happened from ground-based assets in less than 10 years. So it's a very important activity for us. And the last one I want to talk just a little bit about, because I want to not steal my colleague's thunder, is DART. DART is going to be making impact with an asteroid called Didymos on September 26th at 7:14 p.m. Eastern Time, and I hope you will all be watching. And with that, I will turn it over to my colleague from ESA.
Thank you very much. I'll be standing up. So, you had some pretty good backup slides there. So, hello, I'm Richard Meusel from the European Space Agency Planetary Defense team, and it is my privilege and honor today to present to you our activities in space regarding planetary defense and on Earth. In order not to be too redundant with what has been said before by my NASA colleague, it goes along the same lines. So also our mission statement is to find objects in space, to detect them as early as possible and as many as possible. When we've detected them, we sit tight and assess ever so briefly, and then we engage in doing active countermeasures, or at least risk mitigation by warning decision makers and disaster relief agencies. This is also reflected in our structure. This is a little bit of a pictogram. So the Planetary Defense Office of ESA is separated into 3 pillars. It's not really separated, it's organized. The first one is the observational pillar, where we get the data. The second one is the so-called assessment pillar, which is the core piece of our work, where we determine the threat. Is it a threat? Is it just a close flyby? Is it nothing to worry about if we discover a new asteroid? And the third pillar will be the mitigation activities. I'll walk you briefly through some examples of our work. There's plenty of more to come. First of all, the observations pillar. As you can see from this little collage, there is a world map with all the telescopes where we either operate the telescopes, where we have service agreements with the operators, so we are tapped in. But besides that, we are also tapped in, like the NASA colleagues, into the worldwide network of observers and astronomers. Some things to highlight is that we also build our own instruments. On the lower left, you see some weird-looking instrument there. This is the so-called fly-eye telescope. Here we go on a toe-to-toe battle with the laws of physics and with what's feasible in optics, trying to optimize the field of view, sensitivity, and resolution all at the same time. Those of you who work in this field will know that it's a tough battle, but we are making very good progress and hope to be able to construct the first one of these beauties soon. The second pillar is the assessment pillar. Here we have many tools, too many to speak about them today in the brevity of time. However, it goes from, on the left you see the early warning system that already reacts like the NASA counterpart to unverified objects upon first sighting and does a very quick assessment of a threat and is an early warning system. But the hard piece is called Aegis, like the shield of Zeus. This is our big computing program that calculates the orbits of asteroids up to or exactly 100 years into the future. In special cases of special interest, this might even be more, even quite a bit more. The very, very important thing here, which I want to stress, is cooperation is key. If you had one instance in the world doing these computations, you might risk that they are compromised or that they do one mistake or that there is a bug somewhere. So we're not the only ones. We're doing this in very tight collaboration with the NASA colleagues to ensure that we are on the same page, literally, with what's going on in the case of threats. The third pillar is the mitigation pillar. Hera is part of the mitigation pillar because we want to take more data of the asteroids, but we also regularly issue warnings or advertisements, even in case of small impacts or close flybys that might be good to observe in our close approach fact sheets. That's the fancy one that you see in the upper middle. This one is a public service, open for subscription by anyone in the world. This is for all humankind. And you can be warned, everyone can be warned of incoming asteroids, of perilous asteroids, or of interesting things to watch in space. So please make sure you give our webpage a look. For, let's say, for privileged customers or for disaster relief agencies, decision makers, we are right now prototyping and developing an automated warning system which will react even faster and without much human intervention. And of course, stressing again that cooperation is everything, is that we are also, as was pointed out, part of the UN-sanctioned groups, the International Asteroid Warning Network and the Safe Space Mission Advisory Group, in which we participate to the best of our abilities. One big activity in planetary defense is Hera, but Patrick will later on describe this to you in much more detail and way better than I could ever imagine. So I'll just stay tuned. There's some interesting things coming. But also the future of the Planetary Defense Office has some nice things to hold for you. So, of course, we're going to continue with our activities, expand them, make them more robust, make them quicker, make them more precise. That is the normal work. But we've also got some very interesting projects in the future. We have got the telescope array. I talked briefly about the FlyEye. This is the attempt to do one very high-performance high-end monolithic system that is capable of improving the whole fields with 2 or 3 units across the globe. On the other side, the commercial sector has been developing some very interesting concepts so that we are also at the same time in parallel studying the concept of a telescope array where we employ a couple of commercial off-the-shelf hardware and network it in a clever way and in order to complement the existing systems. There's also a commercialization approach. This is a concept under study. Stay tuned for more. This is very interesting. Thank you for presenting NEO Surveyor. So I can save some time. We have a very similar concept. NEOMER is, again, an infrared telescope at the L1 point, as was outlined wonderfully before. However, with a complementary survey strategy. While NEO Surveyor is looking as deep and staring as long as possible to get every one of the really dangerous ones, ours is supposed to scan rather rapidly, compared to NEO Surveyor, with high revisiting times in order to catch the small, close, fast-moving ones. This will be the first ever quick warning system in space on the day side. And I'm looking forward to the cooperation between the two missions because between the two of them, they will get a lot of the unknown population. Very looking forward to this. This is the next big thing in planetary defense as ESA is concerned, or as a lot of things are concerned after Hera. And last, but I would say not least, I don't know if you've heard, but on Friday the 13th of April, 2029, the big asteroid Apophis, 320 to 350 meters in diameter, this is not a small one. This would be way more devastating than the one we've seen in Asteroid Hunters, is not going to impact Earth, but it's going to zoom by so close that from the northern latitudes it will be visible with the naked eye. You don't even need binoculars to see it coming by. It's that big and it's that close up. And we want, together with NASA, who have declared interest in supporting and joining us, we want to launch at least a small mission to encounter the asteroid to deliver to you the real-life equivalent of this wonderful artist's impression. So stay tuned. There will be this and many more things to come. With this, I hand over to the really exciting DART mission.
I got a lovely introduction. So I am here to talk about DART, the Double Asteroid Redirect Test, NASA's first planetary defense mission that was built and operated by the Johns Hopkins Applied Physics Laboratory. I'm Dr. Betsy Congdon, and I am the lead mechanical engineer on DART, and so I'm going to go into the details. As you've heard multiple times now, planetary defense is really a global enterprise, and many partners across the globe made this mission possible. The concept is we are going to go and kinetically deflect an asteroid. Seems simple, right? We're going to target a binary system, Dimorphos, as was mentioned. And so that means that there are two asteroids. We're actually going to go and impact the littler one, Dimorphos, which you see there in the picture. You see DART coming in and hitting it. And it's really neat that we're going after a binary system because we can actually measure the change in the orbital period that we're going to have happen here on Earth. And so that's what's so exciting is we can go, and then we can see it. And you're going to see a lot about how we're going to observe that. Just to kind of get a frame of reference, the DART spacecraft is about 550 kilos on impact. And it's going at 6.1 kilometers per second at the time. Now, we've been talking a lot about this. We're 6 days away from impact. We launched last year in November of 2021. And on Monday is when this impact actually happens, which is so exciting. Along for the ride with us is LiCiCube, which is an Italian CubeSat provided by ASI. And that was successfully released about a week ago and is actually going to watch us come in. So there's a lot of international exciting cooperation. You're probably wondering about all of the numbers that have been thrown around. So here's a scale, just to give you an idea. We like to think of the DART spacecraft as about like a bus, but it's mostly solar rays, as you're going to see. It's going to go and impact Dimorphos, as I said, the smaller of the two asteroids, and that's about 160 meters. So that puts it somewhere between the Statue of Liberty and the Pyramids of Giza. So kind of to get your mind around it. The larger asteroid is about 780 meters. So here's just a nice animation of what I was describing. You can see that we're autonomously guiding ourselves. The spacecraft will be autonomous at this point into the asteroid. And as it goes in and hits, we hope there is ejecta coming out the back. As been talked about, one of the big questions is how, what are these asteroids really made of? Because it matters as to how we might defend against them. And we're really excited to see how much ejecta really does come off because it will matter about how much momentum we can actually transfer during this operation. If we have an asteroid and we just hit, no ejecta, just a little nudge. What if we get a little bit of ejecta coming out the back? It almost acts like a little thruster, so we get a little bit more momentum. And then if you get a lot, it's an even bigger thruster, so we get to go even more. So we're going to see what we're actually going to see in just a week. How do you build a spacecraft that's destined to die in a collision with an asteroid? So this is just some pictures along the way of building up the DART spacecraft. It happened over 2020 and 2021, so it was definitely an interesting experience. This is the spacecraft bus structure coming back from Aerojet Rocketdyne, where the liquid propulsion system was put on it, and it's being installed in the clean rooms at Johns Hopkins Applied Physics Lab, getting ready for the rest of the things to be put on it. The next step is the electronics boxes, the harness, getting all tested and checked out and installed. And here we're installing the main panels that a lot of that hardware was on. One of the key features of DART is the rollout solar arrays, or ROSA solar arrays that were made by Redwire. They're really neat. You've kind of seen them. They're huge. And so this is the day we actually put on one of them. It was a very exciting day. Our one and only instrument, which is the camera that actually is being used to guide ourselves into the asteroid, is Draco, and this is the installation of that camera. And we're actually getting like the asteroid view. If you were standing on the asteroid as they're coming in, this is looking up into the camera. This is what the view will be into the mirrors. So that's pretty neat. LiChaCube getting installed, and as I said, was successfully deployed about a week ago, and that's in its container there. The DART mission was launched on a SpaceX Falcon 9 out of Vandenberg, and so this is the spacecraft all buttoned up and getting ready to be put on the rocket. And then, as I mentioned, we launched in November of last year, and so the team since then has been going through tests and preparing for Impact Day, just 6 days away. This is a picture of the team this month in September doing a dress mission rehearsal for Impact Day. This is just another little overview of the spacecraft. Most of these things I have mentioned, but I will highlight a couple of them that I haven't. DART also has a NEXT-C engine, which is a NASA ion propulsion demonstration on it. I already mentioned that Draco is the main instrument on the spacecraft that is going to be used to actually, the images will be used to guide into the asteroid. And the guidance is happening by SmartNav, a technology development, using those images to actually autonomously guide into the asteroid. And the high gain antenna is a radial line slot array. So it's a really exciting time. We are less than 10 days, so you can see that the end of this chart is not even useful. So we are continuously doing ground antenna coverage at this point, preparing for 6 days from now. Just 8 hours before is when we begin the pre-terminal phase, leading into the actual terminal phase 4 hours before. This is when we're fully autonomous and the SmartNav guidance is enabled. What's really cool is you can see kind of the blurry pixelated images up there on the corner. That's what it's going to look like at that point. That's when we're going to start guiding in. Only 60 minutes before, about an hour before, is when the secondary becomes observable. So we're actually seeing Dimorphos. It's larger than a pixel, starts becoming a thing. The last couple of minutes are their last images where we don't see Didymos anymore and we're just focused on Dimorphos. And you know, in those last seconds is when we actually start seeing what's the shape of this, what's it made of, what are the features on the asteroid. And as has been mentioned, that's one of those questions that's really important to science. And then impact, and one of the only times where loss of signal is celebrated and cheered. So not only is DART itself, you know, an international collaboration, but the observation is as well. You can see that ground-based telescopes across the world will be looking not only at impact, but also the year after, as we study and understand how we affected the orbital period, really changing our vision of how we can do planetary defense. In addition, we do have space-based assets that will be looking at the impact, both Hubble Space Telescope and James Webb. So this is my last slide. I hope that you are as excited about DART as we are. We cannot wait for Monday. On the left-hand side, you can see the coverage that you can follow Monday evening. I encourage you to sign up to be a planetary defender and get a badge proving that you're part of that global organization. Already done. Already done, see? Right. Already done too, so join us. And then please follow along on the social media feeds and the hashtags on the right. Thank you.
Good job.
Thank you. Yeah, it's going to be absolutely exciting. So I'm going to tell you about what follows DART, which is the Hera mission. And for the details, you can come to the technical session on Thursday afternoon. I will give you much more detail because in 7 minutes, actually, I want to put that in the context of the current knowledge about asteroids. And therefore, first, what I want to say is, why do we study asteroids? Why are they so fascinating? And actually, there are at least 3 reasons why we study them. The first one is, of course, a science reason, because they are among the best tracers of the solar system history, because they kept the memory of the original composition of the solar nebula, which is lost in the planets which have heated and have cooked, and they are now a big cake, and you don't have the recipe to make the cake. And asteroids contain this recipe. Then you have planetary defense, because some of them represent a risk. And then you have resources, because many countries and companies are now interested to see whether we could exploit them in order, you know, like use them as gas stations to go further away. And in fact, for all these reasons, you essentially need the same knowledge, which is what are they made of structurally, in terms of chemical composition, and more importantly, how do they respond to an external action in their super low gravity environment. And that's what I want to show you, is that in fact, we need these missions like DART and Hera and other kind of missions that interact with these bodies, because we are still at the beginning to understand how they respond to these kind of actions. So one thing that I think is really striking is when you see this image, you can see that asteroids are not boring space rocks. They are super exciting because they show a great diversity among them. You see on the left side, you have images of asteroids, different shapes, different sizes, different morphologies, absolutely incredible. But on the right side, even on one asteroid, you have a wide variety of geological structures. You find landslides, you find ponds, craters, grooves, boulder fields, even some particles are ejected from some asteroids like Bennu. So it's absolutely incredible, and that tells us something about our history, because these features come from the collisional history of the solar system and other processes which affect them during their lifetime. So we are still at the beginning to digest all this information and to try to understand what it means. And of course, for planetary defense, this is super important to know, because the coupling of the impactor on the surface highly depends actually of what the impactor will encounter on the surface. So if it hits a rocks, it's very different than if it hits a sand beach, for instance. And another thing that I will show you is that, in fact, even with these images, you don't have the whole story, because you may think these surfaces are, let's say, have strengths because you see rocks. That's not necessarily the case, as you will see. So unless you touch the surface, you cannot know what is the mechanical response of the body. So about planetary defense, actually in Europe, we started very early on. It was like almost 20 years ago when ESA solicited 6 experts to recommend space missions related to the impact risk. And we recommended a mission called Don Quixote, which was actually the grandfather of DART and Hera, and we can come back to that a little later. And now we have this IDA international collaboration, which is actually, IDA stands for Asteroid Impact and Deflection Assessment. It's a science collaboration that supports the development and data interpretation of DART and Hera. So you have seen what DART will do, and we are, wow, waiting very hard that it happens, because it's been a long time that we really wanted this mission. And then Hera will come into play on the crime scene, as we say, a few years later, in order to investigate in detail the outcome of the impact, as well as the physical properties of the target, because what we want is to have a fully documented deflection test with both the initial conditions given by DART, the first ejecta given by the Licha cube, and then the final outcome given by Hera, so that the numerical impact models have less free parameters to try to reproduce this experiment, and therefore they can be validated with great reliability, and we can extrapolate this knowledge to other scenarios. So this is really the aim, and that's the aim of this international cooperation. So DART will give us the impact condition in terms of impact speed, impact angle. We know the shape and the mass of DART. And Hera will come to measure the properties of the target that influence the impact outcome, and in particular the mass of Dimorphos that allows us to directly measure the momentum that is transferred by DART to Dimorphos. So Hera will do that. That will allow us to validate the numerical models of impact. As you can see here, these are some simulations which have been validated by confrontation with impact in laboratory. But these impacts are made on centimeter-sized targets. And we now know that we cannot extrapolate the knowledge at small scale to large scale. And one example is the Hayabusa 2 mission that made a crazily great experiment by exploding a box at 100 meters from the asteroid Ryugu. That was a small impact. It was 2 kilograms at 2 kilometers per second. And it was super successful. And what we found is that the crater is about 15 meters, which is much larger than what we predicted if the surface had some strength. So we predicted 2 to 3 meters. And you can see on the left, you see the image before the impact. They are rocks. Rocks for us are solid. And yet, when the impact touched the surface behaved almost like a fluid, like a cohesionless medium, like if there was no resistance. How weird is that? So you could not predict that just by looking at the images. That's why we need impacts and we need to interact. Another example is the OSIRIS-REx mission that also took a sample of the asteroid Bennu. And again, you can see on the left, you see a lot of rocks, boulders, gravels, etc. And when the sampling tool touched the surface, it went down with almost no resistance, like in melted butter. Unfortunately, the thrusters were activated and the spacecraft went away, but it could have gone through, we don't know. And again, we could not predict that. So these bodies have very counterintuitive reactions to external action simply because their low gravity environment is something we don't experience on Earth. And therefore, we need to experiment. That's why we need that. So Hera in the context of Hayabusa 2 and OSIRIS-REx is super important because with DART and Hera, we'll go to an object which is 3 times less wide than Bennu. So we go even lower in gravity levels, and we can see how things scale effectively at low gravity level and with gravity with many implications. So mission of first, that will be the first rendezvous with a binary asteroid, the first characterization of such a small body. You see Dimorphos compared to the largest boulder on Ryugu. This is about the same size. And I must say that one of the challenges of DART is to eat this thing because we don't even know the shape. We just know the size. So you will discover with us on the 26th of September what it looks like. We don't know even us. So the public will have for the first time the opportunity to discover with a scientist a new world, basically. So the mission scenario of Hera is a launch in October 2024, an arrival in 2026. So we arrive a few years later, but nothing will have changed in space, so we can really still measure the outcome of the DART impact a few years later. And then we have 6 months of close proximity operations. This is a spacecraft. You can see all the instruments here. This will be then arriving in 2027, and then we will deploy some CubeSats. One of them, called Juventas, will for the first time measure the internal properties of an asteroid. We never did that. So we'll know whether it is a monolith, whether it is an aggregate, and that will allow us to better interpret what DART will have done on the asteroid. And finally, we will also land one of the CubeSats that will bounce on the surface, and this is another way to measure the mechanical properties of the asteroid, because as I said, it's very important to touch if we want to know what happens. This is the Hera today. You can see in the clean room. Hera emission of first, and then I will end there by saying that understanding collisions is not only important for planetary defense, it's also important for our own history, because collisions played a key role in the solar system history, simply because planets formed by collisional accretion. We grew bodies because the collisions were at low speed enough that when the bodies come together, they just grow and grow and grow. Then we had a giant impact like the moon and maybe Phobos and Deimos around Mars. And now we are in an era where all solid surfaces have craters because simply we are now destroying or cratering the surfaces. And if we want to draw a robust scenario of the solar system history, then we have to understand this process and define reliably what happened when two bodies collide together. And that's where DART and Hera will feed these models because we are at the correct scale. Thank you very much.
Yes, thank you. Greetings, everyone. I'm Bill Nye. Do I need to start this, or does it happen? 3, 2, 1. That's a joke. There, thank you. Yeah, merci. Yeah. Here we go. So, for those of you who don't know the Planetary Society, if you found yourself on an elevator with me, I might say, hi, I'm Bill Nye, CEO of the Planetary Society, the world's largest non-governmental space interest organization advancing space science and exploration so that citizens of the cosmos will know citizens of the world will know the cosmos and our place within it. And then the door would close. So this is a picture from a gathering we called Planet Fest. This is from Curiosity. And I'm there in the middle. And if you know where to look, Elon Musk is there. He was on our board for a while. He recused himself. But we are the non-governmental agency advancing space science, and we are very concerned about planetary defense. So I like to say we do 4 things. We educate. I claim we have the best long-form journalism about space on the web of anybody around. especially in English. We innovate, we come up with projects, I'll show you a couple, to advance our mission and especially to prepare for an incoming asteroid. We collaborate with other agencies around the world, and we advocate. We go to governments and advocate for certain space missions. So the first thing, everybody, is to get the public interested in planetary defense. And many people think, well, if you have an asteroid, you just sort of point at it, give it a push, and then everything would be fine. But as you know, finding them is a very, very difficult part of this. It's, as the saying goes, it's like looking for a piece of charcoal in the dark. They're very difficult to find. So we sponsor people around the world who go looking for them. The big question for everybody is, how does this affect me? And you'll hear people talk all the time right these days about saving the planet. We need to save the planet. The planet's going to be here no matter what we do. I want to preserve Earth for me, for humans. And that's why planetary defense is so important. So if you show people a picture like this, it makes an impression. If an asteroid this big were coming into Paris, that would be the last thing for all of us. Some of you may know I did a podcast for a couple years. We had Joanna Morgan, who's a researcher. She was a co-author on the most recent paper about the Chicxulub crater impact, that the asteroid that probably finished off the ancient dinosaurs. And she pointed out that the thing was coming in so fast that you would probably, I'd never heard this before, you would probably turn all the molecules in the nearby part of the atmosphere to a plasma. And the asteroid, instead of looking like this, would look more like this. Like the sky would turn opaque for several minutes. That's a joke, but we're not going to wait several minutes. Sorry. So we sponsor amateur astronomers around the world. Now, and for those of you who haven't stopped to think about it, amateur astronomers are not like amateur tennis players, in that amateur tennis players don't really contribute to the art and science of tennis too much. But amateur astronomers are scientists who contribute a great deal to the understanding of asteroids. And the big problem with asteroids is finding them, because there are so many of them and they move so fast relative to the background stars, and they're dark. This is Bob Stevens, very enthusiastic amateur astronomer in Australia. We have a very enthusiastic group at the Beppo Forte observatories just north of Naples in Italy. People gather at night and look for asteroids. So over the last several decades, we have given out grants to over 24 people around the world, 24 amateur astronomers around the world, who contribute to the science of asteroid hunting. And they do this because they love it, because they want to find these asteroids. It's fun to go looking for them, and of course it may save the world. So it's just something that we have done. We named them after Gene Shoemaker, who many of you may have known, was a guy that did a lot of the early physics of craters. And he was a big friend of the Planetary Society, and he was there when the string of pearls ran into Jupiter back in the day. So you may know that, that's our education and our outreach, but we also innovate. And you may know we built 2 light sail spacecraft. And light sail, these are solar sail spacecraft pushed through space with nothing but photons. And this is part of our innovation mission. And LightSail 1 launched in 2014. LightSail 2 launched 3 years ago, and it's still flying. And the sun has been relaxed enough that the atmosphere hasn't swollen, and so we're still aloft. And I know all of you are members, and you all follow LightSail 2 on your phones. Thank you. But What's relevant is we developed this deployment mechanism. It seems like a straightforward thing, but deploying these sails, these shiny mylar sheets, is tricky because of you guys build spacecraft, just the nature of mechanisms in zero gravity or low gravity. So Light Sail 2 is about as big as this part of the stage. The solar sail community, this is at California Polytech Institute in San Luis Obispo, California. You can see people in the background. This is a test we did on 4 ping pong tables taped together. But the solar sail community is a small bunch. Les Johnson's not here because his next spacecraft is going to launch on the Space Launch System any week now. And you can see it's about 4.5 times as big as Light Sail 2, but the mechanism's very similar. And we contributed to this effort, and very proud of that. Then Asteroid Day, the 30th of June, as reckoned on the Gregorian calendar. We support Asteroid Day. We try to get people around the world to realize that looking for asteroids and preparing to defend the Earth from them is very important. And I think we could add a little animation to it, you know, because this is based, the 30th of June is the anniversary of the Tunguska event in 1908. And when I was in college, by the way, you guys, I took one class from Carl Sagan. That's why I'm here. He talked about the Tunguska event, but nowadays we figure it was an airburst. It hit the atmosphere going so fast. How fast was it? It was so fast it just disintegrated. And what we do, the big thing we do is, along with Asteroid Day, is advocate. So we have 50,000 members around the world, and I've met many of you, thank you, and we educate our members about how to interact with lawmakers, especially in the U.S. And we go to the U.S. Congress with people who are very well informed. These are our members. These are civilians, not professional space explorers, who have a passion for space. And we have been successful in getting the U.S. Congress, Japanese aerospace, Japanese members, European Space Agency, Canadian Space Agency, getting those agencies to take the threat of asteroids seriously. And I'm very proud to be part of the team, and thank you very much for including me. So the Planetary Society is advancing space science, and we are contributing to planetary defense by getting citizens of the world excited about it. Thank you all very much. We are here, and let's be careful down there. Thank you.
So with that, I know that there's a lot of questions coming in on Slido. I think we're all experts on Slido by now, so keep them coming and keep them upvoting. And we don't have much time, but I'd like to try to get through as many of these questions as we can, so let's try to be a little bit quick about that. So, Richard, I'm going to toss this first question over to you. So the question has to deal with, all right, these spacecraft are really hard to build. Now, what do you actually think is harder, getting the technical work done or getting the political willpower of everybody together to say, hey, this is something worth funding? Let's do it.
That's a very interesting question. I think, speaking as a scientist, doing let's say, the math of what needs to be done, that is the easiest part, because you can always just calculate the energy. Then the engineering is a whole different thing. But humanity has shown over and over again that we are great at engineering things if we hold together. So yes, I would say the holding together, the gathering enough people who pull on the same rope in the same direction, this is the big challenge, and this is something we all need to work on.
Can I add something to that? Von Braun said, gravity is easy to lick, but the paperwork is sometimes overwhelming. I think that kind of applies to this as well. I think, as
very
Richard
nice quote,
said,
yeah.
And I guess
it's
the paperwork,
solvable problems,
right,
if we can get the funding in place, the organization in place.
That's the old saying about people who think the moon landing was faked. Just look at the amount of paperwork
Yes.
If you were going to fake the moon landing, it's warehouses full of documents.
No one fakes that amount of paperwork.
All right, thanks. So next question, we're going to bring it over to DART. So we saw how big or small the target is. So what testing have we done to make sure we're going to hit this thing? How confident are you? How confident is the team?
Yeah, the team is really confident we're going to hit it. I mean, it is hard. This is really hard. That's why we do the things we do. But many practice missions, looking at contingencies, understanding what might happen. It's hard, but we're confident we're going to do it.
All right.
You're stopping a bullet with a bullet.
And everybody, you can tune in on Thursday morning, actually. Betsy's going to be giving a late-breaking news session where she's going to give us the pulse of the DART team in the Mission Operations Center right now. As you know, they're in 24/7 ops right now, so it's a really exciting time. Here you can hear the latest and greatest from Betsy in a couple days. So the next question I'm going to head over to talk to Bill about. Now, quick show of hands out there. How many people have seen the movie Don't Look Up on Netflix? So hopefully everybody here, or else you're in the wrong plenary session. So I personally loved it. Now, one of the things we saw in there was the wonderful / not so wonderful reaction of all the people. No, there's no rock there, don't look up. It's right there. How realistic do you think that is, given the climate that we're in today?
How do we do that? We get people excited about it. Everybody loves space exploration. And so we just get people where they are. An asteroid threat is a very reasonable thing. When I was in school, when I was in elementary school, no one had a good idea of what happened to the ancient dinosaurs. I remember my teacher reading to us from a big book, dinosaurs had small brains, so the mammals took all their food. Yeah, Tyrannosaurus rex versus rabbit. Yeah, like Tyrannosaurus, rabbit. Yeah. No, even she knew that was horrible. But in my lifetime, the asteroid impact off Chicxulub it's the best idea we've had. So we just get that message out as much as we can. Space exploration brings out the best in us. It's where we solve these problems that have never been solved before. Let's go, people. Let's save the world.
Let's do it.
Let's go.
Applause. Thank you. Yeah.
Can I add something about this? Can I add just quickly something about it? Yeah. I think this is a good question. I mean, the scenario of Don't Look Up is realistic. Of course, a long period comet is super improbable. Most of the objects that impact the Earth are actually asteroids coming from the main belt. And should we worry? I would say we don't need to worry because, of course, this is a very low probability risk, but with high consequences, and for all the known objects, none is threatening us. However, we know that on the long term, it will occur again because we know the impact frequency. And what we know also is that for these kind of low probability events with high consequences, it's better to be ready before we need it. Because improvising is super risky and we should not take this risk. And the good thing with this risk is that this is one of the only natural risks that we can predict and prevent with reasonable and feasible means that were implemented. So it's only a positive message that we are trying to define a robust plan that the future generation can use without having to improvise, because we see how complex it is. Predicting means sending a spacecraft, and if any surveyor can go, in 10 years, we can really be able to identify whether we have an imminent risk, probably no, and we will be in better place to anticipate it. And preventing it is to making the test that we are doing with deflection. And then there is the other aspect, the political decision, the international coordination, so that we have a coordinated response at international level. And that is done at the UN nations. So we are currently doing all these steps. We know it takes time. In principle, we have time, but it's better to do it so that we don't have to improvise when it happens, and fortunately, on the long run.
I mean, even if you find one, you need 30 years, right, or 20 years.
That's a perfect segue to my next question right there. So if we did find one, and we're putting up all these new assets in the near future to seek these things out, what if we did find one on a collision course that was something in 3 years, not 30 years? What do you think we can do about that? I'm going to head that over. Other than that, that's not the most helpful response. So,
Make a big budget.
So the fact that it's 3 years out says to me two things: that we actually haven't launched Neo-Surveyor or Neo-Mir. So that's a good cautionary lesson. The other thing, it actually tells me that if it's 3 years out, that it's probably not a very large civilization-ending asteroid, because those we know mostly where they are. We know when if they might hit, and we kind of sort of know that is not a scenario we are in.
The big ones, we got those covered. Right?
But the key word is probably. It's probably wouldn't be world-ending.
Yes,
That's good.
But since we are talking probabilities, I think it's more likely that this is this is a small asteroid. Mm-hmm. This is and again, to Bill's point, a Paris ending or New York ending asteroid is nothing to sneeze at. It's very important that we address it. 3 years is not enough time for us to launch a disruption mission or even a deflection mission. I would say in the 3-year timeline, we would characterize the asteroid, better understand it, and then actually see, prepare for airburst impact or prepare for a hit essentially. One thing we could do, depending on the size, is send a nuclear mission, but that's obviously a very complicated scenario. So my best recommendation is let's make sure that doesn't happen. Let's launch Neo-Surveyor. Let's launch Neo-Mir. Let's get DART in place so we can have, once we have these assets in place to detect, characterize, track, we will know 10 years ahead of time, and then we can deflect them, and that's a scenario we want to be in.
Absolutely. So we don't want to be in that situation where we only have 3 years. If so, put your houses on sale if you're in the unfortunate damage zone. So I think with that, can we go to the next slide here? I wanted to leave you guys with a short trailer of what to expect over the next week. Betsy talked a little bit about DART and all the new technologies that's on there. You're going to see a movie that's going to show those rollout solar arrays. You're going to see the opening of the camera door for Draco, so the spacecraft can actually see where it's going. You're going to see the Italian contribution CubeSat leading all the way up to the event that we're all looking for in less than a week. Hit play. Yeah, I just realized a couple minutes ago that the clock here is counting up, saying that we're over time. I thought we had 3 minutes to go, but we have 3 minutes over time. Just want to leave you guys with a couple closing thoughts really quick. So yesterday, for those of you that attended that highlight lecture, you heard a little bit about the Parker Solar Probe and the ESA Solar Orbiter mission. 2 missions, NASA and ESA, working together. You heard 2 scientists from both teams talking about the different perspectives, the different literal vantage points from a literal perspective, as well as perspectives where they're coming from, to give us a new understanding of space weather. It's one of the hazards that we have to deal with. Here you've heard a lot about the collaboration between NASA and ESA on the DART and Hera missions. These collaborations don't just happen, right? They happen because of people getting together, the right people getting together at conferences like this, having those exciting conversations to spark those ideas, and then they continue those conversations over time. So I encourage you guys, as this Congress continues through the week, especially all the young people here. Make those contacts, do all that networking. It's not just a buzzword, it really matters. Because you never know what conversations are going to spark the next big deal. What's the next big thing that we're going to do? And hopefully one of you guys will be sitting on this stage 10 years from now at the 83rd International Astronautical Congress, encouraging people to do the same thing. So let's get out there, have a great Congress, and thank you very much. Bye-bye.